Good morning, people. Rare form today, really rare form. We're going to be talking about the very last section of this derivatives content that we've been doing. And the first thing we're going to tackle is going to be a review question based on yesterday's topic of being able to find the slope of the tangent line. So remember that our definition of that is that the derivative of any function is going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h. And let's apply this particular idea to this one right here, which is the x cubed deal. I'm going to pause the video at this point in time, fill out this particular derivative, and come up with the slope of the tangent line. And then we can talk about some of the pieces that are inside of it and where we're going to be going from here. Now, I paused at this particular location because, as you can quite see, that once I plug in x plus h into the cubed function, this piece right here starts to get to be a little bit cumbersome. And I wanted to show that we have actually seen some of this stuff before, that when we raise a binomial to a higher power, we could possibly use the binomial expansion theorem or maybe Pascal's triangle. So I'm going to do a little Pascal's triangle here off to the side, and 1, 3, 3, 1, and I'm be looking for the third row. I know that looks like the fourth row, but remember that this is the 0th row. I don't know if that's a real word, but this is the third row. These are the coefficients that would be in front, so technically that upstairs cubic, if expanded with the binomial expansion, would end up being 1x cubed. Then we would do a combination of the two where this one would get smaller and the h would get bigger. So that would be 3x squared h plus 3xh squared plus h cubed minus the x cubed down here on the end. So you can see even Pascal's triangle could be something that could be coming back into the mix when it comes to finding determinants. Now, if I approach this going to 0, again, the bottom is a problem. Let's see if there's any cancellations that take place. And that would be these cancel out. The h could be stolen from everything that's upstairs. And if you can see a little bit ahead on this one, if you steal the h out of each one and cancel it with the bottom, we'd be left with 3x squared plus 3xh plus h squared. And again, we're talking about when this limit is approaching, this limit as h is approaching 0, well, that would cancel these two guys out based on the 90% rule, and we'd end up with a derivative of 3x squared. Now, based on finding the slope of the tangent line at a specific location, the derivative evaluated at 2 would be 3 times 2 squared, and the slope at that particular location would be the number 12. And that's the slope that would be going on. Okay. Now, when you're probably looking at many of these problems, you're just like, man, gee, they are long and they are tedious. And ultimately, going from something like this very long derivative concept and squeezing it down to this derivative answer did take a little bit of algebra to end up getting there. Now, your question probably is there some kind of shorter way? And I don't want to say that there's a shorter way, but there is definitely places that we can cut the fat is really what we're going to do here. And that means that there's got to be, in terms of shorter ways, there's got to be some concepts out there that maybe make finding these derivatives relatively easy in terms of that there are certain, what am I going to say, certain rules that can work here. Now, what I want to say is that many of the things that we've been working on have been basically written as polynomials. So what I mean is that we've been talking about things like 3x cubed or maybe even 5 over x, something like that, which really could be written as 5 times x to the negative 1 or so forth, or 6x to the 6x plus 5. Okay, now let me give you a kind of a basic ballpark deal here. is that each one of these answers, I could find their derivatives relatively quickly. This guy's derivative is 9x squared. This guy's derivative, and we'll just do a different color right here. This guy's derivative is negative 5x to the negative 2. And last but not least, this one's derivative is 6. Okay? Now, how am I coming up with those derivatives so quickly? And that is that there happens to be a power rule that's inside here. It's one of many rules that you learn in terms of finding derivatives. There's a lot of different rules that go into derivative the way you come up with a derivative. And this one happens to be what's referred to as the power rule. Now, the way that this works is that if you're dealing with a polynomial, and polynomials are ones where they have a coefficient, a variable, and a power that's written up above, is that you do this operation. I'll just kind of like highlight this, and let's do green. I think green is good. What you do is you take the power, you multiply it times the coefficient that's in the front, and then you reduce the power by one value when it comes out here. So if I did 3 times 3, that would be where the 9 came from. And then the power is reduced by 1, and that's why it became the number 2. Now let's try it again on this one. Now it doesn't really work well when it's written as a rational expression, but if I write it as a power in terms of polynomial, I can actually go these two times each other, which generates the negative 5, and then this guy gets reduced by 1. That would be negative 2. And now we take a look at this last one. That's 6x to the 1. 1 times 6 gives me the 6. And then this guy reduced by a power would end up making it 0. Now, what happened to the 5? And the 5 ends up turning out to be a rule that when we take the derivative of a constant, it ends up disappearing. We end up getting nothing. There's nothing here. It's an empty space. Now, later in calculus, we'll put a variable there. We'll probably put plus c, some kind of value that's going on down there. But ultimately, at this point in time, the derivative of any constant is nothing. It doesn't exist, okay? So we'll put this kind of stuff in as we start to talk about antiderivatives and integrals when we see them later, because we're going to try and find a way to get back to the original function. Now, with that in place, now we can start looking at some of these questions with a little bit better concept. And if I say I wanted to find the derivative of that particular function's derivative would be, again, the derivative of each individual part. And this would be the top times the front, which would be 2x, and then this would be reduced by 1 power, so that'd be 2x to the 1, or just 2x, plus, and then we do the derivative of the second part just as easily, and that's to the first power, so 1 times 3 would be 3, but then this would be changed to 1 minus 1, which would be 0, and it would just be 3. Check it out. That is the derivative of the whole thing. Now, if you could verify that if you wanted to go back and do it the whole entire long way, but the power rule is verified by that concept. Now we can try a couple of questions where it's at x equals negative 2. Let's find out what the derivative of that is. You're probably thinking, man, gee, why didn't you just show us the power rule in the beginning? And that isn't how math works. Math works in a way where we have to have a concept that we come up with before we can jump to shortcut rules that allow us to make the problems a little bit more manageable. Okay, so we're talking about the derivative at f of negative 2 would be the number negative 1. And then we would also talk about x equaling negative 3/2. The derivative at that location would end up being 2 times negative 3/2 plus 3 on that, and then these would cancel, and we'd end up with the number 0. Now, let me basically talk about what this means in terms of what are these answers really telling you. You're like, okay, so what does this mean? Now, let's remember that what you're doing right here is a derivative. You're taking the derivative's answer. If I was just finding f of 2, I'd be plugging it into the original function, and I'd be basically getting an answer of, and I'm just going to push this up so I can see it, of, come on, go up, of 2 squared, which is a 2 squared plus 3 times 2, and I'd end up with a 4 plus 6, or I'd get the number 10. Now, this is completely different than what I'm finding down here. When I'm doing it just with the original function, I'm really plugging in a domain of 2, and I'm getting out a range of 10, and this really constitutes a point that's on the original function. Now, when I do it over here and I'm plugging in -2 into the derivative, yeah, I'm actually plugging in -2 into the derivative, and it is still a domain, but what I'm getting out on the other side is not necessarily, it's a range, but the answer that you're getting right here is, let's remember what the derivative is finding. It is the slope of the tangent line. And what I'm saying here is that you're getting a slope in this y location. Even though it looks like a point, it is technically saying that at -2, the slope is -1. So if I was going over here to say this particular point, which is -3/2, comma 0, I basically be saying that at the domain of -3/2, the slope is 0. And if I was thinking about that on the original graph, let's say the original graph is a parabola, and I'm going to take that little parabola and do little things with it. I'm going to say x squared plus 3x, and I'm going to take the x out and get x plus 3. And I'm going to say, oh, if I set that equal to 0, I can get a couple of x-intercepts. That's going to be 0 for one of them, and it's going to be -3 for the other one. So this parabola would come down like this, and it would end up coming back up like that. So I've got a basic function shape. What this particular question is saying is that at -3/2, right here, halfway between those two intercepts, the vertex happens, and at that vertex, the slope of the tangent line is 0. And that's what the derivative is really saying. So in essence, when we write this derivative function up here, we're really writing in its own right another equation for the slopes at those particular given lines. Now, here's a better example of what I'm trying to focus on. And this is what your mind needs to really be kind of like thinking about. Now I'm going to move this off to the side right here, and I opened up this applet. Now this applet basically shows functions. The original function that's being done here, this is a cubic function that you guys can see, and we've done these in Algebra 2 and so forth. But what the applet is going to do right here is on this slider, I'm going to be able to slide this slider, and it's going to move along the domain, and it's going to see the, you might be able to see it. It's a light blue line right there that's showing the tangent lines at those particular locations. Now, what it's drawing up here is it's drawing the domain that we're sitting at right there. That's the same domain as where that guy's being drawn. But what it's doing is it's writing what the slope is. See how the slope right here is 5.43? Well, that 5.43 is up here at 5.43 in terms of a y range. So it's basically changed it from the x-axis on this green graph. X-axis is domain, but the y-axis is a representation of the slopes because it's graphing the derivative. Now, you can see that as you graph this thing, the slopes are going up, and as soon as the slope becomes 0 right there, you're probably going to see that this particular derivative has finally hit 0 on the x-axis because it's 0 for the y piece or the slope in that particular graph. And as we start to slide along, now it's going to become negative, and now it's going to start to turn. This particular slope right here is starting to turn because the derivative is still negative. It's still going down. But the moment that it goes past this location, it's going to end up becoming positive again because the slopes are slowly but surely changing in terms of where they're not decreasing anymore. This is still decreasing in terms of slope. When we get here, the slopes start to rise again because it's starting to flatten out. And we get to this particular inflection right here where this vertex would be, this localized vertex, or localized minimum, that's probably a better answer for it, that it's back to 0 again. And then the slopes start to rise again. And then we get going on right here. Now, what we're really seeing is that if I was doing this cubic function right here, we saw this cubic function in that original deal, its derivative is a parabola or an x squared. Now I'm going to go back to our original function right here that we were doing at the beginning, and we saw that the original function was a cubic right there. That concept was a cubic, but its derivative down here, oh, don't undo that, undo that. Its derivative in this location was a square, or better yet, a parabola. So what you're really getting when you do these derivatives is you're getting equations for a representation of all the slopes over that particular set of domains. So kind of think that, yeah, it's a derivative, but more importantly, that derivative that you're generating right here, this guy right here, this derivative, is an equation for all of the slopes over all the domains of the original. All right. Now, you're going to have to kind of play around with that. You're going to see on that applet, there's all kinds of funny ones that you'll basically see. So like if I pick another example, like, hey, here's a 4th power polynomial, which would mean that its derivative based on the power rule would be a cubic, because we would multiply the front and reduce the power. Let's see if it looks like a cubic. So as we come along right here, here comes the domain coming down, and you can see that the derivative of a 4th power polynomial is a cubic function. We'll kind of keep taking a look here. Well, what would be the derivative of a line? Well, as you came across with the slopes would never change going all the way along here. The slope is always going to be 2, and that is why the derivative of a linear function, I'm going to go over here to a linear function. That particular graph is like, say, y equals x, something like that. Well, its derivative would be, well, if this is a power of 1, that would go out into the front. It would just be 1, okay? So this just happens to be that the slope of that line is 2, and the derivative would be a constant. It would be a solid line, and it would be represented that way. So you can see that what you're drawing right here is really the answers to those two derivatives. Now let's think about this one. This is going to be a negative slope all the way down to here, and then it's going to be a positive slope going on like that. So the derivative would be negative for a while. Then when it gets to here, it'd be 0, and then it would pop up to 1 on the other one, and it'd be a step function in terms of doing a type of deal when it comes to an absolute value. If I was doing, say, this hill type, which is a rational function, let's see if we were talking about it's positive, it's positive, it's positive, and then it would become something like that. That's what the derivative would be. Now, we've got the power rule to help us with some polynomial ones, but this is not polynomial anymore. This is a different kind of concept. So we would have to have other rules that would help us understand this. Like, here's a logistics graph. And this is kind of like relates to what we've been talking about when it comes to the pandemic. So this concept right here is the exact concept of a logistic graph of what we would expect to happen in terms of a pandemic. You get people that would grow in terms of exponential growth of people getting the coronavirus, and then there would be a herd mentality, a herd concept, meaning that nobody else is able to get sick because everybody is sick, okay? And what we would like to see is what happens to the graph as we draw the derivative to it. Well, the derivative is an example of what is the slope or the amount, a rate of change of the people that are getting sick. And this is exactly what they've been talking about on the news about flattening the curve, that if we extend the domain or push the time out further for this logistic graph, that this particular derivative or the a rate of change of the amount of people that are getting sick would slowly flatten, and it wouldn't end up exceeding the amount of people that could be in the hospital with ventilators. So in kinds of like a real concept, this graph right here is exactly what you're experiencing right now when it comes to your stay home policy for the coronavirus. And that's what the statisticians are really hoping for. An upside down or absolute value, maybe even coming up with, this would be a sine wave. What would be the derivative of the sine wave? Well, the derivative of sine looks a whole lot like cosine. There's something going on there in terms of the actual height of the amplitude does come into play too. So we're going to have to learn other rules when it comes to trig, because they're functions too, and turning out to their concepts. This right here, I don't remember what this one's particularly called. There's a function for this one, but if you were to graph it, you can see that the graph is more or less an inverted concept to it, is what's going on. An upside down hill, this is a rational expression. An upside down W, an upside down W might be something that's related to a cubic again, and you can see that the cubic is just inverted, is all that's really going on in terms of that. The upside down there, maybe a sine wave. You can see a little bit more of the sine wave in terms of the fact that it is a cosine wave that's related to the derivative. An upside down W, again, would be a inverted cubic. Same kind of idea going on there, and that just repeats. So you're getting the idea that what you're doing here is really more of a focus on what is the slope doing over any given domain. Now, be aware, you might be actually asked, in this particular case, you're asked to go from the function to the derivative. But as we well know, that math is not a one-way street. You might actually be asked that I'm giving you some information about the derivative later, and you might have to go backwards and think, what does that mean on the original function? What is that derivative telling me is happening on that original function? And this is where your brain has to start to think about, what are the graphs really doing? All right, now let's apply that power rule in terms of finding the derivative. I'm going to shorten these questions down a little bit, finish them up, and hopefully we'll get a little bit more out of this. So power rule based on this, power rule multiplied by the front would end up making this 3x. But remember that the power will reduce by 1, so it's 3x squared. And the derivative of a constant doesn't actually have a derivative, so there's your derivative. And there was no long way to that one anymore. You've basically got a now power rule that applies to polynomials, and you can pull that off. Now let's find out what's really happening at x equals -1. And we're going to apply the derivative at -1, which would be 3x squared, and I'm going to do 3 times -1 quantity squared, which would be 3. And then if I checked it at 1, I'd be able to say that the derivative at 1 would be 3 times 1 squared, which would be the number 3 too as well. Now, here's a question. Why are they the same? Well, if I was thinking going backwards here, the original function was a cubic, and I'm going to try my best to draw this cubic. I know that it crosses at -2. And what I'm basically saying is at -1, and I know that probably drew this too high, at -1 on the domain, the slope down here at that spot was the number 3 is what was going on there. And then over here at the number 1 it was here at the same spot. Its slope was the number 3 as well because it was listed at 3 on the range. Because remember that when we're graphing the derivative's y is about the slope of the tangent line. So we basically be able to say that the slope of the tangent line at those 2 points in the domain is parallel. And we would be getting the same exact amount of velocity at either one of those 2 spots. Now we can start saying velocity, we can start saying acceleration, because again, calculus is very relatable to physics. And that's one of the reasons why we teach physics and calculus at the same time, because the concept can be very relatable. Okay. Now you're probably asking, okay, how am I going to tackle a square root in terms of maybe using the power rule? And here's what I want to say first is that can you represent a square root as an exponential power? And you absolutely can. This is x to the 1/2 plus 2. And now you're starting to see those connections of polynomials and rational expressions are starting to come back, and they become important that you've got that mental math stuck inside there in muscle memory and see what's going on. Now, this would be 1/2 rate x, but then this reduces by 1 full power, so it'd be to the negative 1/2, and the derivative of a constant is not going to exist at all. Now, you're probably like, a negative power would mean that that concept would be on the bottom, so you could write this question as 1/2, but this whole expression for the exponential would be downstairs, or x to the 1/2 downstairs, or we could write it as 1/2 raised to the 1/2 root x would be the derivative. Now, I didn't have to go through the long way to get this one. This one's kind of a bummer to do the long way, but the power rule makes it much more consumable. What would happen if I evaluated that derivative at 4? I'd get 1/2 times the square root of 4, or that answer would be 1/4. There's your slope of the tangent line at that location. Or if I wanted to find the derivative at 1, I would say that that's 1/2 times the square root of 1, and that answer would be 1/2. Now, I'm going to put an extra one in here. What if I put in that I wanted to find the derivative at -1? And that answer would be 1/2 times the square root of -1. And you would end up with that the derivative doesn't exist. And it doesn't have an answer. And that makes sense because domains of -1 don't even exist on the original function. So why would the slopes of the actual original function, where it doesn't have any answer to it, have an answer in terms of its derivative either? So concepts that are relatable there make sense that certain domains that work on the original would not be domains that would work on the derivative. Okay, now let's find the derivative again and find out what we would deal with here. So that's the original is f of x equals 8/x. Well, that could be represented as f of x is equal to 8/8x to the -1. And that derivative would end up being using the power rule. Notice I wrote it as a polynomial. This times this, which would be -8. And then I would reduce the power by 1, which would be -2. And if I wrote that back in its original function, it'd be -8/x squared. And now you've got yourself the derivative to it. So let's see here. What would it be as x is equal to -2? And x at -2 for the derivative would be, why my control key is being pushed. There we go, fix that. -8/2 quantity squared would be a -8/4, which would be -2. Even if I evaluated that derivative at 1, let's see what we get here. We get -8 divided by 1 squared, which would be -8. And we're talking about slopes of tangent lines at that particular deal. Now, something we haven't seen in a while, this is going to be the slope that you found. But what if the question wanted the equation of the tangent line at that location? Well, again, to find the equation, we're going to use the point slope form of the equation, which is y1 minus y1 equals m times x minus x1. And you're probably going to note, you're going to be like, wait a second, what point do I plug in? I definitely have a slope, which is -2. I do have a domain, which is x minus -2 in there. But where's the y coming from? And that's why we would have to use this to go back to the original and generate the original coordinate, which is going to be -2 comma -4. And that would be the number that we would want to plug in for that point that's on the graph. And that equation would be y plus 4 would equal -2x. And that's a plus right there, but it's going to be -4. And if I subtract 4, I'll end up with y is equal to -2x minus 8. And this would be the equation of the tangent line at that particular point of domain. And see, notice that it does have the slope that we're supposed to expect from the derivative, but we get the y-intercept by plugging in a point into that point slope form. Okay. Now, what your real goal here is to really get some practice, first off, probably with your power rule, but really to understand that this is really just an intro to what you're going to see in terms of calculus. There is so much more to explore here, like all those derivatives of functions that we didn't get a chance to cover, like how do you do your trig functions and find their derivatives? How do you find a logistic graph? How do you find a logarithm or a natural log in terms of its derivative? There is a lot of derivative work that can be done, and understanding how derivatives work backwards and learning how to integrate will be another part of calculus that you're going to see. So there is a large portion of this that you get to explore. So it kind of opens up a brand new world of how all the family of graphs that you guys have been doing in the past and how we're going to relate those to physics, how we're going to relate those to slopes, how we're going to relate those to volumes and surface areas. And calculus really opens up big time doorways into helping you understand a lot of the fields that are out there. I mean, we can talk about biology, we can talk about the sciences, we can talk about engineering. Calculus really does do a lot for us. And you really should take an advantage of going after it, because at your level of mathematics at this point in time, you really should at least explore some of those concepts that are based on in calculus. So keep trying and keep working on this, and I hope you're getting something out of these videos, and keep trying those. Have a great weekend, Huskies, and keep staying safe and keep learning, because we're super excited about the work you guys are doing.